Hello everyone, my name is Gao Ying from Hebei University. The topic of my research is dynamic specification mining based on transformer. Our main purpose is to mine high-quality software specifications. Software specifications play an important role in the life cycle of software development. Software specifications accurately describe the operation of the program and ensure the high quality of the software, have the ability to help developers understand the code and check that it meets functional requirements. It is clear and easy to locate errors for easy management, as well as able to reduce the cost of software maintenance and so on. When writing software specifications, it is difficult to describe the interface relationships between the components of the software and between the various stages of development. In addition, software specifications described in natural language have problems such as ambiguity, redundancy, and confusion between levels of abstraction. Below is a motivation. Software specifications should be documents that can make complete and precise statements in a verifiable way. Formal methods are ideal modeling tools that enable smooth transitions between different software engineering activities and can provide a means of high-level confirmation. For example, a finite state automata can describe the order in which methods are called through different states and transitions between states. Automaton models are more precise and abstract than natural language descriptions. The precision of the expressions help to make the specification clearer. However, the existing software specification model is of lower quality. For example, the key-tail algorithm is the basis for many techniques that are made based on the FSC specification. It merges each pair of states with the sequence of the same method in the next key terms. However, this consolidation is imprecise for stacks of different capacities. Although the key-tail model is incomplete because the traces of method pair that happen to be called in a particular order but don't to be called. Besides, Karka et al. Proposed the mining techniques in order to evaluate the principle behind existing specification mining techniques, such as Contractor++, ICKT, and TMI. However, the resulting specification model is not precise enough. In 2018, David Low et al. Proposed the deep specification miner, which is called DSM for short. It uses deep learning to gradually improve the accuracy of the model, but the built language model of recurrent neural networks performed poorly when processing long sequences. In order to solve the above problems, we use the transformer framework as a feature extractor on the basis of the DSM, because the transformer can capture the temporal dependencies between input and output, and can improve the feature extraction ability of long sequences. The transformer is a full tensor mechanism. It is able to selectively focus on areas that need to be focused on. By quickly scanning global information, we get the target areas. Then, more attention is invited in this area to get more detailed information about the targets and to suppress other uses information. Here's our workflow. The first is to get a rich set of execution traces. Through the traces, a transformer model is built as a feature extractor. In addition, extracting the trace subset of the execution traces and importing the trace subset into the transformer model for feature extraction. and then the extracted features are represented by a series of feature values. The feature values are entered into clustering algorithm to merge the values with similar features to obtain multiple simplified automata. Finally, selecting the best performing automaton as the final specification model. Each step is explained in detail below. The first step is trace generation, using the test case generation tool RunDup to generate test cases, executing test cases, and getting a set of execution traces. Each execution trace is a sequence of method calls, where start and end are the flags for the beginning and the end of the sequence, taking all prefixes of each sequence as states and creating a chain representation for these states. The second step is to learn a transform model based on the collected set of execution traces. Given a theoretic method to be called, the model can predict the next method that can be executed. For example, we use a trace like this as the input to the transform model. At the point, the previously predicted method is start. Enter this method prefix, predicting the probability of each method occurring, and it is represented by a logic vector. Using this vector as the feature value of the method prefix. As we mentioned earlier, each prefix is treated as a state. That is, the feature value of this state is the logic vector. We take the method which has the probability and add it to the method prefix to predict the next possible method. For example, when the method prefix is start, the next most likely method to appear is stack AR. Add it to the method prefix. At the point, the method prefix is start stack AR, and then the prediction is made through the transform model, and the next most likely method is make empty. The make empty is added to the method prefix for the next round of prediction. Until the identity end is predicted, this round of prediction ends. The next step is to extract the subset from the execution traces. This step is to improve mining efficiency and reduce computational costs. For example, if we want to extract a subset from these three traces, we first need to extract the pairs of methods carried by the three traces and count the number of occurrences of each method pair. Querying the shortest trace of method pair with the first occurrences successively and adding it to the trace subset until the trace subset contains all the method pairs that have appeared in all traces. Experiments have shown that the quality of the specification model that extracts a subset of traces by adjacent pairs is almost the same as that of the model made using the other traces. Therefore, this handling is feasible. The next step is feature extraction. In this step, we extract two feature values to provide more information. The first one is the logic vector for each state obtained using the transform model, logarithmically processing the elements in it. The second one is represented by the position of a method that has already appeared in its current state. If it doesn't appear, the feature value is 0. The feature value not only illustrates if a method is present, but also provide information about the location of the method. Next, it is cluster analysis for merging similar states. The goal is to create a more simple and general-purpose automaton to capture the specification of the target library class. We use k-means, hierarchical, and dbScan clustering algorithms. K-means is a division cluster. It is simple and easy to understand and implement. The convergence is faster and efficient. The hierarchical clustering algorithm adopts a bottom-up aggregation strategy to form a tree-like clustering structure. Dsm-T is a density-based clustering algorithm that can cluster any shape of a dense dataset. K-means and hierarchical clustering require a predefined number of clusters. We try to search for the best FSA from all the automata generated when the number of clusters is 2 to 20, because the cluster number of 1 is meaningless. The clustering algorithms yield a total of 2 multiplied 20 subtract 1 plus 1 FSAs. Among them, K-means and hierarchical clustering algorithms generate 20 subtract 1 FSAs. Dsm-T clustering algorithm generated 1 FSA. For example, the flowchart is an FSA with a file number of clusters generated using hierarchical clustering. After that, it is model selection. In this step, we use the same evaluation criterion as one measure as the DSM, where in the precision formula, this represents the number of method pairs carried by the 3 traces, and this represents the intersection of the method pair carried by the traces and the presumably FSA. Precision represents accuracy of the generated automaton, which contains the fewer redundant pairs of methods and better accuracy. The recall represents the completeness of the generated automaton. The TR in the formula represents the number of traces, and the accepted traces represents the number of the traces that FSA can accept. The more traces an automaton can accept, the higher completeness will be. We use the existing set of public execution traces from specification mining to facilitate comparison with existing tools. We use 11 target library classes to evaluate the effectiveness of our tool. The target library class lists all the names. The M column represents the number of methods defined in the target class. The recorded method calls represents the number of methods logged in all traces for the target class. We compare our tool Dsm-T with Dsm and for other dynamic FSA inference techniques, including K-tail, ICKT, Contractor++, and TMI. K-tail stands for trace-only strategy, which means that the model is inferred only from execution traces. Contractor++ stands for invariant-only strategy, which means inferring the model only from invariant. ICKT is a technique that infers the model from the execution traces and then strengthens the model with invariant. And TMI infers the model from invariant and enhance the model by execution traces. The results of experiments are shown in the table, showing the F1 measure of the final FSA generated by each tool. The results show that for all library classes, 1-tail, 2-tail, ICKT1, DSM, and Dsm-T can output the final FSA. ICKT2, Contractor++, and TMI failed on 2, 4, and 6 classes. On average, all F1 measure finally reaches 93.13% of the DSM, which is 21.16% higher than the best performing DSM among the other 7 instruments. Using the transformer framework, our research proposed and implements a technique for mining software specifications dynamically and names it Dsm-T. The accuracy of the specification model is improved by evaluating our results through experiments. Previous research has demonstrated that the model generated from invariant strategy that combine two types of execution information are more executed than the models that use one type. Therefore, I plan to add invariant information to the specification model generated by Dsm-T to further improve the quality of the specification model. That's all. Thank you.